This is the reason the universe might look completely empty even if it isn't. And it comes down to something almost embarrassingly simple. Everybody might be showing up to the party after everyone else has already gone home. Not because life is rare, not because we're alone, because timing, on a cosmic scale, is brutally unforgiving, and civilizations may simply be missing each other by hundreds of thousands, or millions, or even billions of years. If that idea grabs you the way it grabbed me, stick around, because by the end of this, you're going to understand exactly why the sky can be full of life and completely silent at the same time, and why some of the smartest people working on this question today think we might actually be one of the earliest guests to arrive. And if you want more of these deep dives into the biggest unanswered questions in science, go ahead and hit subscribe. Drop a like on your way out. It genuinely helps this channel keep making them. Let's start with the question itself, because it didn't begin as a formal scientific theory, published in a journal with careful footnotes and peer review. It began as an offhand comment made over lunch by a man who apparently never wrote a single word about it afterward. In the summer of 1950, 4 physicists were walking to Fuller Lodge at Los Alamos National Laboratory in New Mexico, on their way to eat. Enrico Fermi was one of them, along with Edward Teller and Herbert York, who had recently arrived at Los Alamos while the lab was in the middle of a crash program to build the world's first hydrogen bomb. A 4th physicist, Emil Konopinski, joined the group partway through the walk. The conversation had turned, of all things, to flying saucers, which were dominating headlines and public conversation at the time. Only months earlier, a retired naval aviator named Donald Keyhoe had published a widely read book called The Flying Saucers Are Real, arguing that the military was hiding what it knew about UFOs from the public. Konopinski had also just read an issue of The New Yorker featuring a cartoon that joked about aliens stealing municipal garbage cans, a nod to a real rash of garbage can thefts happening in the area at the time. So by the time the 4 men sat down together, extraterrestrials were already the running joke of the meal. Somewhere in that conversation, sitting at the table, Fermi asked a question that would end up outliving every other detail of that lunch. According to the recollections of the men who were there, recorded years later by other researchers piecing the story back together, Fermi worked through the logic out loud, more or less the way a physicist does when a puzzle catches his attention. If the universe is as big as we think it is, and stars are as common as we think they are, and life is even remotely likely to evolve on some fraction of the planets orbiting those stars, then there should be an enormous number of civilizations out there, and at least some of them should be far older and more advanced than us. Old enough, advanced enough, to have had time to spread across the galaxy already. So where is everybody? That question is now known as the Fermi Paradox, and it has become one of the most famous unresolved puzzles in all of science. But here's a detail most people don't know, and it's the kind of thing that quietly changes how you think about the whole debate once you hear it. Fermi never actually published anything on the subject of extraterrestrial life or interstellar travel. Not a paper, not an essay, not a single line in any of his scientific writing. Everything we know about what he said at that lunch comes entirely from the memories of the people sitting at the table with him, memories that were only written down and compared years afterward. Historians who have gone back and carefully reconstructed the event, cross-checking the recollections of Konopinski, Teller, and York against each other, have pointed out that crediting this entire idea to Fermi is a little bit like crediting Newton with discovering gravity because of a falling apple. It's a good story. It has just enough truth in it to survive, and it makes for a much cleaner legend than what actually happened, which was messier, more casual, and more human. What actually happened next is that the question sat there for about 25 years, mostly as folklore passed between physicists, before anyone turned it into a rigorous, structured argument. That happened in 1975, when physicist Michael Hart published a formal paper making the case in detail. Hart argued that if a civilization ever developed the technology for interstellar travel, spreading across an entire galaxy wouldn't actually take an unreasonable amount of time. He estimated that this kind of galaxy-wide expansion, colonizing world after world, star system after star system, could realistically happen within a time frame of just a few million years. A few million years sounds like an almost unimaginable stretch of time to a human being living roughly 80 years. But measured against the age of our galaxy, which is somewhere around 10 billion years old, a few million years is nothing. It's a rounding error, a blink, barely a fraction of a percent of the whole timeline. So Hart's conclusion was blunt and honestly a little chilling. If extraterrestrial civilizations existed anywhere with any kind of meaningful head start on us, they should already be here, or at the very least, their engineering, their structures, their signals should be detectable somewhere in or near our solar system. Since we haven't found anything like that, Hart argued, the simplest and most direct explanation is that there isn't anybody else out there to find. That is one answer to the paradox, and it is a genuinely grim one, because it suggests we are functionally alone in a galaxy of 400 billion stars. But it is far from the only answer, and it is not even close to the most interesting one, because buried inside that same basic logic is a much stranger, and honestly, a far more haunting possibility. This possibility doesn't require life to be rare at all. It only requires life, once it appears, to be spectacularly poorly timed relative to everyone else. Here is the way to actually feel the scale of this problem, rather than just hear the numbers. Imagine the entire history of the universe compressed into a single calendar year, with January 1st representing the Big Bang and midnight on December 31st representing this exact moment, right now, as you're listening to this. On that calendar, our sun doesn't even form until early September. Life on Earth doesn't show up until sometime in late September. Multicellular life, the first organisms made of more than one cell working together, doesn't appear until early December. The dinosaurs, which dominated the planet for well over 100 million years, go extinct on December 29th. Human beings, in any form we'd recognize, don't show up until the final hour before midnight on December 31st. Every single thing you've ever learned about in a history class, every pyramid, every empire, every war, every book, every love story, happens in the last 60 seconds before midnight strikes. And radio technology, which is currently the only method we have for either detecting or announcing intelligent life across interstellar distances, has existed for a fraction of a single second on that same scale. Now take that same calendar and stretch it across every other star system in the galaxy at once. Hundreds of billions of them, each one running on its own private version of that same clock, starting and ending at different points depending on when their star formed and how quickly life evolved there. Ask yourself a simple question. If 1,000 different civilizations each got their own 60 seconds of technological visibility, scattered randomly somewhere across that same enormous year, what are the actual odds that any two of those 60-second windows would land on top of each other? The honest mathematical answer is that the odds are terrible, vanishingly small. You could have a galaxy absolutely packed with intelligent life, civilization after civilization rising, thriving, building cities and telescopes and questions of their own, and eventually fading back into silence, and you could still end up with a sky that looks completely, totally empty, simply because nobody happened to be shouting into the void during the exact same sliver of time that somebody else happened to be listening. This general idea, sometimes called the cosmic timescale explanation, is one of the most quietly devastating answers to Fermi's question, precisely because it doesn't require aliens to not exist. It only requires the universe to be exactly as big and as old as we already know it is, and civilizations to be comparatively short-lived. Researchers studying this problem have pointed out that humanity itself has existed as a species for roughly 200,000 years, but we've only been actively listening for radio signals from other worlds since around 1960. 200,000 years of existing, and about 65 years of actually paying attention to the possibility that someone, somewhere, might be talking to us. If even one other civilization out there went through a broadly similar pattern, existing for thousands or millions of years, but only broadcasting or listening during a tiny sliver of that total time, the chances that their sliver would land directly on top of ours are somewhere between slim and essentially none. This exact idea has a formal name in the academic literature that almost nobody outside the field has ever heard of. It's called the interdice hypothesis, and it comes from a paper published in 1987 in the respected planetary science journal Icarus, titled Temporal Aspects of the Interaction Among First Galactic Civilizations. The paper looked specifically at the timing problem rather than the distance problem, arguing that even if civilizations turn out to be common throughout the galaxy, the real bottleneck standing between us and contact isn't how far apart we are in space. It's how far apart we are in time. Space, however enormous, is at least theoretically static. Distances can eventually be crossed, given enough patience and enough technology. Time only moves in one direction, and once a window of opportunity closes, it stays closed permanently. A civilization that rose and fell 3 million years ago isn't just far away from us. It's gone, in the most absolute sense that word can mean. There is no catching up to it. There is no sending a message that could possibly still find anyone home on the other end, no matter how loudly you shout or how long you wait for a reply. More recent researchers have tried to take this idea and actually model it with mathematics, rather than just describing it in prose, which is where things get even more interesting. A pair of scientists, I. Bezudnov and A. Snarsky, built something called a cellular automata model, essentially treating the entire universe as a kind of enormous grid, with civilizations appearing on that grid as individual objects that grow, sometimes interact with their neighbors, and eventually die out. What they discovered was a nonlinear threshold behavior in how the total presence of civilizations changes across both time and space, which is a fairly technical way of saying that the mathematics itself backed up what the interdice hypothesis had already suggested using plain language. Civilizations are born, they develop, some of them reach what you might reasonably call a golden age, and then, eventually, they die. Dying, in the context of this model, doesn't only mean total physical annihilation, the kind of thing you'd picture in a disaster movie. It can also mean a civilization simply losing interest in reaching outward toward the stars. It can mean their technological development stalls out for reasons that have nothing to do with catastrophe. It can mean they stop transmitting, stop actively searching, stop caring about what else might be out there the way they once did, and quietly turn their attention inward until, from the perspective of anyone watching from a distance, they look exactly like nothing was ever there to begin with. There's an even more unsettling variation on this same basic idea, sometimes referred to as the burnout hypothesis, or more formally, the asymptotic burnout model. The researchers behind this framework argue that once a civilization becomes fully connected, essentially transforming into one single, interlinked global society, the kind of thing humanity itself is arguably becoming right now, with the internet and global communication, it hits a kind of structural ceiling. The pace of technological and social change starts accelerating so rapidly that the amount of time available to solve each new crisis before the next one arrives keeps shrinking, year after year, decade after decade. Eventually, according to this model, that gap between crises becomes smaller than the actual time it takes to invent and implement a solution, and something inevitably has to give. Either the civilization collapses under the weight of its own acceleration, unable to keep pace with problems that are arriving faster than solutions can be found, or it recognizes what's happening in time and deliberately chooses to slow down, to prioritize long-term stability over relentless, unchecked growth. And here is the part that connects directly back to the silence sitting over our heads every single night. A civilization that makes that second choice, the one where it turns inward and consciously stops chasing expansion for its own sake, stops looking like an empire spreading outward across the galaxy. It stops broadcasting at full volume. It becomes, from a distance, essentially invisible, not because it failed, because it succeeded at something other than conquest. And success, in this case, doesn't leave the kind of fingerprints a radio telescope can pick up. Now, to really understand just how thin our own window of visibility actually is, it helps to look at what humanity has actually sent out into the universe so far, because the real numbers involved are almost comically small when you put them next to the true size of space. Humanity's radio footprint had its real practical beginning on December 24, 1906, when the inventor Reginald Fessenden made what's considered the first intentional, powerful radio broadcast, a transmission that famously included a recording of Fessenden himself playing the violin. That signal, along with every radio signal broadcast after it, has been traveling outward from Earth at the speed of light in every direction, continuously, ever since. It is still traveling right now, this very second, further from our planet than it was when you started watching this video. But there's an important distinction worth making here between intentional transmission and targeted transmission. Fessenden's broadcast, like the vast majority of radio and television signals humanity has ever produced, wasn't aimed at anyone. It leaked into space simply because that's what radio technology does by nature, whether you mean for it to or not. The first time humanity deliberately aimed a message at another specific star system, on purpose, with the explicit intention of it being received by someone else, didn't happen until 1974, with the transmission of the Arecibo message, broadcast from the massive radio dish at the Arecibo Observatory in Puerto Rico, aimed toward a distant star cluster tens of thousands of light-years away. Everything before that moment, and honestly the overwhelming majority of everything since, has just been leakage, television broadcasts, military radar systems built during the Cold War, signals blasting outward into the void, not because we meant to announce ourselves to the rest of the galaxy, but simply because that is an unavoidable side effect of using radio technology at all. So how far has all of that accidental leakage actually traveled by now? This is where you'll find some genuine disagreement between different sources, and it's worth being upfront about that, rather than pretending there's one single, clean, universally agreed upon number, because the estimate depends heavily on exactly what you're measuring, which signals you're counting, and even what year the calculation itself was made. One widely cited estimate places the outer edge of our detectable radio bubble at around 120 light-years, based specifically on those very earliest, faintest experimental broadcasts from the early 1900s. But the stronger, more consistently powerful signals, the kind that would actually stand a real chance of being picked up by a hypothetical alien receiver on the other end, didn't really begin in earnest until around 1950, when Cold War-era military radar and high-powered analog television broadcasting both ramped up dramatically across the industrialized world. That stronger signal sphere is estimated at closer to 76 light-years across, which might sound small in the grand scheme of things, until you realize it has already washed over real, specific, named stars that exist in our night sky. Vega, roughly 25 light-years from Earth. Altair, roughly 17 light-years away. Somewhere out there, in a purely hypothetical sense, the electromagnetic echo of 1950s American television broadcasts is, right now, sweeping past those exact stars, decades after we originally sent it out, without ever intending for it to go there at all. Other estimates, built using slightly different assumptions about signal strength and detectability, put the total diameter of Earth's radio bubble at somewhere around 238 light-years, with a radius of roughly 119 light-years. And here's a detail that almost nobody talks about, but that I find genuinely fascinating once you sit with it for a moment. That bubble isn't a solid, uniform wall of signal moving outward through space, like a wave from a stone dropped in a pond. It's better described as a thinning shell. The earliest, faintest broadcasts form the very leading edge of that shell, way out at the front of the expansion, while the stronger, more numerous signals from later decades trail along behind them, layered like the rings inside a tree trunk. And there's a strange irony buried inside all of this. As humanity gradually shifted away from old-fashioned analog broadcasting and toward fiber optic cables and tightly focused digital transmission, we actually started leaking far less energy out into space than we used to during the middle of the 20th century. Which means, in a strange and almost poetic way, Earth was probably at its loudest to the rest of the universe sometime around the middle of the 1900s, and we have quietly been going dark again ever since, even as our own technology has kept advancing in every other respect. Now compare all of that to the actual size of the galaxy we happen to live inside. The Milky Way is roughly 100,000 light-years across, from one edge to the other. If our entire radio bubble is somewhere around 240 light-years in diameter at most, that means humanity's total audible footprint, everything we've ever broadcast, intentionally or not, covers something like 0.002% of our own galaxy. Not 2%, 0.002%. We have been broadcasting our existence outward for well over a century now, and in galactic terms, we have barely managed to clear our throat. Researchers at Cornell attempted to calculate something a little more optimistic out of these same basic numbers, estimating that our radio waves may have theoretically already reached as many as 75 separate star systems, containing at least 29 potentially habitable exoplanets by this point in time. That sounds genuinely exciting, right up until you remember the inverse square law, which is the basic physics rule stating that signal strength drops off in proportion to the square of the distance it travels. Double the distance, and the signal doesn't just get weaker, it gets 4 times weaker. By the time even our loudest, most powerful broadcasts reach a distance of just 100 light-years, they have already faded to a level that is essentially indistinguishable from the ordinary background static of the universe itself. In other words, even in the most optimistic possible scenario, even if there really is a civilization sitting right there among those 29 potentially habitable worlds Cornell identified, they would need almost unimaginably sensitive equipment to ever pick our old television broadcasts out from the ordinary cosmic noise surrounding them. This is the exact point where the timing argument and the raw physics argument collide, and together they make the silence feel less like a mystery and more like something close to an inevitability. Even if another civilization exists close enough to theoretically hear us, and even if they happen to be listening at precisely the right moment, our signal might already be too faint by the time it actually reaches them for it to matter at all. And that's assuming their instruments are pointed in exactly the right direction, tuned to exactly the right frequency, operating during exactly the right decade of their own civilization's history. Every single one of those conditions has to line up, on both ends of the exchange, at the same moment for contact to actually happen. It is less like searching for a needle in a haystack, and more like searching for a needle in a haystack that only exists for one single afternoon, hidden somewhere inside a barn the size of an entire solar system, while blindfolded, using nothing but your sense of touch. And yet, there is one single moment in the entire history of the search for extraterrestrial intelligence that still makes scientists a little breathless whenever they talk about it, because for exactly 72 seconds, it genuinely looked like the needle had actually been found. On August 15, 1977, the Big Ear radio telescope at Ohio State University picked up a narrowband radio signal, meaning a signal concentrated tightly onto one very specific frequency, rather than spread out broadly across many frequencies, the way ordinary natural cosmic noise usually is. The frequency it was detected on sat close to 1,420 MHz, which happens to correspond to the hydrogen line, the exact frequency naturally emitted by hydrogen atoms scattered throughout the entire universe. For decades before this event, scientists had already theorized that if any alien civilization wanted to send a signal specifically designed to be recognized by other technological species, this particular frequency would be an obvious and logical choice, because any civilization advanced enough to have developed radio astronomy in the first place would already be intimately familiar with this exact number. It's practically a universal constant, baked directly into the underlying physics of the cosmos, not something that requires a shared language or shared culture to understand and recognize. The signal itself lasted 72 seconds, which happened to be the exact amount of time it took to pass through the telescope's fixed field of view as the Earth rotated slowly beneath the stars that night. It was strong, it was remarkably clean, and it came from the general direction of the constellation Sagittarius, specifically from a region near the globular star cluster M55. Several days later, an astronomer named Jerry Eman was sitting down to review the printed data from that night's observation, a long continuous scroll of numbers and letters representing raw signal strength across the whole survey, when he spotted it sitting there in the printout. He grabbed a red pen sitting nearby, circled the anomaly right there on the page, and wrote a single word in the margin beside it. Wow. That word stuck permanently, and the event has been known ever since, in scientific papers and popular articles alike, as the wow signal. Here is the detail that keeps this particular story alive nearly 50 years later, long after almost everyone involved in the original detection has either retired or passed away. It has never happened again. Astronomers pointed their instruments back at that same exact patch of sky, over and over, in the weeks, months, and years that followed the original detection, hoping for any kind of repeat or confirmation. They found nothing, no follow-up, no second signal, no pattern of any kind. The Big Ear telescope itself kept running its dedicated SETI survey continuously, night after night, from December of 1973, all the way until it was finally shut down in December of 1997, a 22-year uninterrupted run that remains to this day the longest continuously operating search for extraterrestrial intelligence in the entire history of the field. And in all 22 of those years, spanning literally thousands of nights of careful observation, nothing else quite like the wow signal ever showed up in the data again. In 2020, a Spanish astronomer named Alberto Caballero used data collected by the Gaia Space Observatory, a European mission mapping the precise three-dimensional positions of roughly 1 billion of the brightest objects in our sky, to identify a specific sun-like star that might plausibly have been the original source of the signal. It was a genuinely exciting lead, the kind of breakthrough SETI researchers wait decades for. In 2022, the Breakthrough Listen project, one of the best-funded and most technologically sophisticated SETI efforts currently in existence, pointed serious, sensitive instruments directly at that exact star to check Caballero's hypothesis for themselves. They found nothing, no matching signal, at any wavelength, from that star or from anywhere in its immediate surroundings. The trail, once again, after everything, went completely cold. Nobody alive today actually knows what caused the wow signal, and it's entirely possible nobody ever will. It could have been some kind of natural astronomical phenomenon that we simply don't fully understand yet, something related to comets or interstellar gas clouds that happened to mimic an artificial signal by pure coincidence. It could have been some form of terrestrial interference here on Earth that accidentally resembled what an alien transmission might theoretically look like. Or, and this is the possibility that keeps SETI researchers up at night in the best possible way, it could have been exactly what it appeared to be on that printout back in 1977, a real, deliberate, or accidental signal, sent by someone or something, that happened to sweep across our small corner of the sky for exactly 72 seconds, during the exact window we happened to be listening, never to repeat again, because whoever or whatever originally sent it wasn't sending it specifically to us, and had no particular reason to ever send it in our direction a second time. If that really is what happened, then the wow signal isn't evidence against the timing problem we've been building toward this entire time. It is the timing problem, captured perfectly in a single moment, preserved on a single piece of paper, with one word scrawled in red ink right beside it. Modern efforts to finally solve this puzzle have only grown more ambitious in the years since. In 2015, an initiative called Breakthrough Listen was formally announced to the public, backed by roughly $100 million in private funding provided by Russian billionaire investor Yuri Milner, with physicist Stephen Hawking personally involved in the project's public launch before his death in 2018. The broader Breakthrough Initiatives organization, the umbrella group overseeing this and several related projects, also counts Facebook founder Mark Zuckerberg among its founding supporters. Breakthrough Listen set out to accomplish something no previous SETI effort had ever attempted at this particular scale, systematically observing radio waves originating from within our own galaxy, scanning 1 million of the nearest stars to Earth, and studying 100 of the closest external galaxies beyond our own, all in the ongoing hunt for any signal that might indicate the presence of a technological civilization somewhere on the other end. The project moved into full operations in 2016 and was originally designed to run for a full decade of continuous observation. Researchers like Sophia Sheikh, working out of Pennsylvania State University, have led teams specifically dedicated to going back and re-examining old, unresolved anomalies like the wow signal using thoroughly modern instruments and modern analytical techniques, in the hope that vastly improved technology might finally succeed where comparatively primitive 1970s equipment simply couldn't. So far, after everything, after all that money, all that dedicated telescope time, all that painstakingly collected data, the honest answer remains exactly the same as it's always been. Nothing confirmed. Silence. But silence, as we've been building toward across this entire discussion, might not actually mean absence. It might simply mean bad timing, playing out on a scale so large that it becomes almost impossible for a human mind to hold on to for more than a few seconds at a time before the whole concept starts slipping away and feeling abstract again. Let's slow down and try to make all of this genuinely concrete for a moment. Imagine, somewhere out there in this galaxy, on a planet orbiting a star we haven't even catalogued yet, a civilization did everything right. They evolved intelligence, the same way we did here on Earth. They developed agriculture, then writing, then mathematics, and eventually electricity and radio technology of their own. They pointed their own version of a big ear telescope up at their own night sky and wondered, in exactly the same way we do right now, whether anyone else out there was listening back. And let's say they broadcast, loudly and consistently, for a few hundred years, roughly the same rough window of time humanity has actually had access to radio technology so far. Then, for whatever specific reason, whether it was war or environmental collapse or a societal shift towards some new communication technology that simply doesn't leak into open space the way old-fashioned radio does, or simply a collective choice to stop shouting outward and turn their attention inward instead, their broadcasting eventually stopped completely. And let's say all of that happened 3 million years ago, give or take. 3 million years sounds like an almost unfathomable stretch of time from where we're sitting right now. It is enormous, in any ordinary human sense of the word. But the galaxy itself is roughly 10 billion years old. 3 million years amounts to less than a rounding error measured against that scale, a fraction of a single percent of the total timeline. Their signal, that few hundred-year burst of radio noise representing an entire civilization's brief moment of technological visibility, would have already swept past us and kept right on traveling, long before humans had even developed the physical ability to walk fully upright, let alone the technology needed to build a telescope of our own. We would have absolutely no way of ever knowing that civilization existed. Not because they weren't real, not because they weren't loud, genuinely loud, during their own particular moment, simply because their moment and our moment never actually touched. Now flip the entire scenario around. Imagine a civilization that hasn't even been born yet, quietly forming right now, made from the same raw chemical ingredients that are still swirling around some young, unremarkable star, somewhere out along the Orion arm of our galaxy. If life takes a few billion years to evolve into something recognizably intelligent, the way it did here on Earth, and radio technology takes another substantial chunk of time to develop after that, then we could very well be broadcasting our own existence out into a universe that simply doesn't have a listener there yet, on the receiving end. Not because there's no one out there over the full span of cosmic history, simply because their particular turn hasn't come around yet. This is exactly what the researchers behind the Great Filter concept were really grappling with, even though their framing of the problem was slightly different from the purely timing-based explanations we've covered so far. Economist Robin Hanson, who was a research associate at Oxford University's Future of Humanity Institute, published an essay dated September 15, 1996, titled "The Great Filter, Are We Almost Past It?" Hanson's central argument was that somewhere along the path between lifeless, inert matter and a fully expansive, galaxy-spanning civilization, there must exist at least one incredibly improbable step, a filter so restrictive and so unlikely to be cleared that it alone could explain why the universe looks empty, even though the raw statistical odds strongly suggest it shouldn't. Hanson mapped out roughly 9 major steps that life would need to successfully pass through, one after another, to get all the way from simple chemistry to interstellar expansion, the formation of a habitable star system in the first place, the emergence of simple self-replicating molecules, the jump to single-celled life, the much harder jump to complex multicellular life, the eventual emergence of genuine intelligence, the development of tool use, and finally, the arrival of a technological, spacefaring society capable of reaching other stars. And the deeply uncomfortable part of Hanson's entire argument was this: we don't actually know which of those 9 steps is the truly hard one, the bottleneck, the filter itself. We don't know whether the Great Filter sits safely behind us in our evolutionary past, meaning humanity has already beaten the worst of the odds and the road ahead is comparatively clear, or whether it's still sitting somewhere out in front of us, meaning something is eventually going to stop us, the exact same way it has apparently already stopped, or at least significantly delayed, everyone else. This connects directly back to the timing problem we've spent so much time building up, because the Great Filter and the cosmic timescale explanation aren't actually competing theories that cancel each other out. They can both be true simultaneously. If the filter really does sit mostly behind us in our own evolutionary history, meaning the genuinely hard, rare part is simply getting from basic chemistry all the way up to intelligent, technological life, then civilizations that successfully clear that hurdle might still turn out to be relatively common across the full span of cosmic history. They simply wouldn't be common at the same time as each other, because each individual civilization clearing that filter is essentially an independent, random event scattered unpredictably across billions of years of galactic history. Some clear it early, some clear it late. Almost none of them, statistically speaking, clear it at the same moment as their nearest neighbors, purely as a matter of chance. The Drake equation, which astronomer Frank Drake first laid out formally in 1961, in preparation for a scientific meeting held at the Green Bank facility in West Virginia, actually has a single variable built directly into it that speaks precisely to this exact problem. The equation combines several distinct factors multiplied together: the average rate of star formation across the galaxy, the fraction of those stars that actually have planets orbiting them, the fraction of those planets capable of supporting life in the first place, the fraction that actually go on to develop life, the fraction of that life that eventually becomes intelligent, and the fraction of intelligent life that develops the specific technology needed to transmit detectable signals out into space. All of those individual variables multiply together to estimate n, the total number of civilizations currently existing in our galaxy that we could theoretically communicate with right now, at this exact moment. But there's one more crucial variable folded into the equation, conventionally written as the letter L, and it represents the average length of time a civilization continues actively broadcasting detectable signals before it either destroys itself, falls permanently silent for some other reason, or otherwise stops transmitting altogether. That single letter, L, is arguably the single most important variable in the entire equation, and it's also, frustratingly, the one variable we know the absolute least about, because we only have exactly one example to study in any real detail, and our own personal value of L is, quite literally, still being written in real time. If L turns out to be small, meaning civilizations typically only broadcast for a few hundred years before falling silent one way or another, then N, the actual number of civilizations we could theoretically talk to right now, could end up being tiny, even inside a galaxy that has been genuinely teeming with life across its full 10 billion year history, not because life itself is rare, because the broadcasting window each civilization gets is comparatively short, and short windows, scattered randomly across 10 billion years of galactic time, mostly just don't overlap with each other. It's worth pausing here for a moment on how strange all of this really is, because it flips the entire emotional weight of the Fermi Paradox completely on its head. Most people hear the phrase, "the universe is silent," and immediately assume it must mean, we are alone. But the timing explanation suggests something almost the exact opposite, and honestly, something a good deal more haunting once you really let it sink in. It suggests the universe could be, or could have already been, absolutely full of life, full of civilizations that built their own cities, wrote their own history, made their own art, argued about their own politics, fell in love, made their own mistakes, and eventually vanished, each and every one of them entirely unaware that they were sharing a galaxy with countless others, separated not by distance, but purely by time. Different flickers of the same candle, none of them ever lit at the same moment. Now, the Great Filter and the Drake equation aren't the only serious attempts scientists have made to explain the silence, and it's worth walking through a few of the other major contenders, because each one adds another piece to the overall picture, and a couple of them connect back to the timing problem in ways that are genuinely surprising. One of the earliest and most enduring alternative explanations is known as the zoo hypothesis, first proposed in 1973 by John A. Ball, a radio astronomer working out of MIT's Haystack Observatory. Ball published a short paper in the journal Icarus, the same journal that would later publish the interdice hypothesis 14 years afterward, arguing that the only sensible way to explain the complete lack of interaction between us and any advanced extraterrestrial civilizations is to assume that they already know we're here and are deliberately choosing to leave us alone. Under this framing, humanity is effectively living inside a kind of cosmic wildlife preserve, or a zoo, observed quietly from a distance by civilizations far more advanced than our own, who have collectively agreed, whether through some kind of formal arrangement or simply out of shared ethical instinct, not to interfere with our natural development. Some advocates of the hypothesis go even further, suggesting we are deliberately shielded by something like a one-way mirror, where advanced civilizations can watch us, but we remain fundamentally unable to detect them in return. It's an appealing idea, in a strange way, because it doesn't require us to be unusual or flawed. It only requires that whoever is out there has decided, as a matter of principle, that young civilizations deserve the right to develop on their own terms, without outside interference. Critics of the zoo hypothesis have pointed out a real structural weakness in the idea, though, one that's worth mentioning honestly rather than glossing over. If intelligent life really is common throughout the galaxy, then it almost certainly evolved independently, over and over again, in wildly different environments, under wildly different pressures, producing civilizations with wildly different values, temperaments, and priorities. Getting every single one of those independently evolved civilizations to agree to the exact same policy of silence and non-interference, and to actually stick to that agreement indefinitely, without a single exception, starts to look less like a plausible galactic norm and more like an almost impossibly coordinated act of restraint. It would only take one civilization, somewhere, at some point, deciding to break that unspoken rule for the entire hypothesis to collapse. A darker and considerably more unsettling variation on this same basic idea is known as the dark forest hypothesis, a term that entered popular science discussion largely through Chinese author Liu Cixin's 2008 science fiction novel of the same name, although the underlying concept had already existed in earlier scientific literature under different names. The dark forest hypothesis suggests that advanced civilizations may indeed exist in genuine abundance throughout the universe, but that they remain deliberately silent and carefully hidden, not out of politeness or ethical restraint, but purely out of fear. The logic runs like this. In a universe where you have no way of reliably knowing another civilization's intentions, technological capability, or level of aggression, announcing your own location and existence to the rest of the galaxy is an enormous, potentially fatal gamble. If even one civilization out there happens to be significantly more advanced than you, and happens to view any rival intelligence as an inevitable long-term threat to be eliminated before it can grow dangerous, then the single safest strategy for every civilization, everywhere, is to stay completely silent and to strike first and decisively against anyone foolish enough to reveal themselves. Under this framing, the universe becomes something like a dark forest at night, full of predators, where making noise is the single most dangerous thing any hunter can possibly do. An earlier, closely related version of this same fear, sometimes called the berserker hypothesis or the deadly probes scenario, was described by astronomer and science fiction author David Brin in a widely cited 1983 essay titled The Great Silence: The Controversy Concerning Extraterrestrial Intelligent Life. Brin pointed out that it would only take a single sufficiently advanced and sufficiently hostile civilization to build something called a von Neumann probe, a theoretical type of self-replicating spacecraft capable of endlessly copying and upgrading itself as it travels from star system to star system, to potentially explain the entire Great Silence on its own. If even one such civilization decided to build automated probes specifically designed to seek out and quietly eliminate any emerging technological civilization before it could grow into a genuine threat, those probes could methodically spread throughout an entire galaxy over a comparatively short span of cosmic time, silencing new civilizations almost as soon as they became detectable, long before word could ever spread or any kind of galactic community could form, Critics of this particular hypothesis have raised a fair counterpoint, though. If hostile, planet-sterilizing robotic probes really were spreading through our galaxy on that kind of scale, we would probably expect to see at least some indirect evidence of their activity: unusual energy signatures, dismantled planets, or stars behaving strangely. And so far, we simply don't see anything like that either. A considerably stranger, and in some ways more optimistic, explanation is known as the estivation hypothesis, first proposed in a paper published on April 27, 2017, by researchers Anders Sandberg, Stuart Armstrong, and Milan Cherkovich. Their argument draws on the biological concept of estivation, essentially the summer equivalent of hibernation, where certain animals go dormant during periods of extreme heat rather than extreme cold, and applies it to the behavior of extremely advanced civilizations on a cosmic timescale. The core idea is genuinely clever. According to a principle in physics known as Landauer's principle, the amount of useful computational work you can extract from a fixed amount of stored energy actually increases dramatically as the background temperature of the surrounding universe drops. Since the universe itself is very slowly cooling as it continues to expand, an extremely advanced civilization interested in maximizing the total amount of computation, thought, or activity it can ultimately squeeze out of its available energy reserves might actually make the rational choice to power down now, storing its energy carefully, and wait, patiently, for the universe to cool much further before waking back up and putting that energy to use. Under this framework, the silence we observe today isn't necessarily evidence of absence at all. It might be evidence of extraordinarily long-term, extraordinarily patient planning, on a timescale so far beyond ordinary human comprehension that it barely resembles anything we would normally think of as a civilization's behavior. All of these hypotheses, the zoo hypothesis, the dark forest, the berserker scenario, the estivation hypothesis, the great filter, and the timing-based explanations we started with, are really just different attempts to answer the same underlying question from different angles. And to properly evaluate any of them, it helps enormously to actually know how many potentially habitable planets are out there in the first place, because the entire debate changes depending on whether habitable worlds turn out to be rare or common. This is where NASA's Kepler Space Telescope enters the story. Kepler launched in March of 2009 as part of a mission that cost roughly $600 million, with a single, extremely focused purpose: to stare continuously at one fixed patch of sky, monitoring the brightness of more than 190,000 stars simultaneously, watching for the tiny, telltale dips in brightness that occur when a planet passes directly in front of its host star from our point of view, a detection method known as the transit method. Over the course of its primary mission, which ran from 2009 to 2013, monitoring a roughly 115 square degree patch of sky in the constellations Cygnus and Lyra, Kepler identified an enormous number of planet candidates. By the time NASA released its complete 4-year dataset in June of 2017, Kepler's total had climbed to 4,034 candidate planets, of which 2,335 had already been confirmed through follow-up observation using other telescopes and techniques. Among those, roughly 50 were identified as near-Earth-sized planets, orbiting within their star's habitable zone, the specific range of orbital distances where conditions are right for liquid water to exist on a planet's surface, with more than 30 of those 50 already confirmed at the time. Other independent analyses of the Kepler data have arrived at broadly similar conclusions using different statistical methods. One detailed study, analyzing Kepler's first 3 years of observations, identified over 3,500 transiting exoplanet candidates, with roughly 100 of them sitting inside their star's habitable zone, and calculated that the underlying catalogue carried a reliability rate somewhere between 85 and 90%. A separate statistical analysis, extrapolating from Kepler's early observational data, estimated that roughly 34% of Sun-like stars, specifically stars in the F, G, and K spectral classes similar to our own Sun, likely host at least one terrestrial, habitable zone planet of their own. If that estimate holds up, it implies that something like 1 out of every 3 Sun-like stars in the galaxy could, in principle, have a planet sitting in the right place for liquid water, and therefore potentially life, to exist. It's worth being honest here that later reassessments using newer data, including analysis combining Kepler results with measurements from Europe's Gaia mission, have suggested some of these habitable zone candidates may not hold up as well as originally thought, with certain well-known candidate planets downgraded to marginal or likely false alarms upon closer statistical scrutiny. Even accounting for that necessary caution, though, the broader picture Kepler helped establish remains intact. Planets, including small, rocky, potentially habitable planets, appear to be genuinely common throughout the galaxy, not rare exceptions. That number matters enormously for everything we've discussed so far, because it tells us the raw ingredients for life. Habitable planets orbiting stable stars are not the bottleneck. If there really are tens of billions of potentially habitable planets scattered across the Milky Way, and if even a small fraction of them ever produced intelligent, technological life at some point across 10 billion years of galactic history, then the timing explanation becomes even more compelling, not less. A galaxy with a scarcity of habitable planets might reasonably be expected to be quiet, simply because there's nobody there to make noise. A galaxy with tens of billions of habitable planets, and still nothing but silence, points much more strongly toward a timing problem, or a filter problem, rather than a simple absence of raw material. While all of this searching and calculating has been happening, humanity has also, on a handful of occasions, tried actively reaching outward, sending a small piece of ourselves out into the silence, just in case anyone happens to be listening on the other end, now or at some point in the very distant future. In the summer of 1977, the same year the WOW signal was detected, NASA launched the twin Voyager 1 and Voyager 2 spacecraft on what would become a grand tour of the outer solar system, and eventually interstellar space itself. Attached to each of the two probes is an identical golden phonograph record, assembled by a committee led by astronomer Carl Sagan, designed specifically as a message and a time capsule for any advanced, spacefaring civilization that might one day encounter it. Curating the record's actual contents took the committee, which included Sagan, Frank Drake, writer Anne Druyan, artist John Lomberg, and science writer Timothy Ferris, the better part of a year, and involved an enormous number of difficult judgment calls about what, exactly, represents humanity's greatest hits. The finished record contains 115 images, encoded in analog form, along with spoken greetings in 55 different languages, beginning with Akkadian, a language spoken in ancient Sumer roughly 6,000 years ago, and ending with a modern Chinese dialect. It includes natural sounds recorded here on Earth, surf, wind, thunder, birdsong, and a recording of whale song captured off the coast of Bermuda in 1970. It includes music from Bach to Chuck Berry, and the final spoken greeting on the entire record, recorded in English, came from Sagan's own 6-year-old son at the time, Nick Sagan, who simply said, "Hello from the children of planet Earth." NASA calculated that the record's protective aluminum casing would be able to withstand roughly 4,000 tiny impacts from cometary dust and debris before either spacecraft eventually left the solar system entirely. And Voyager 1 is currently the single most distant human-made object in existence, having long since crossed into interstellar space. Neither Voyager probe is actually headed toward any particular star system on purpose, but current trajectory calculations suggest Voyager 1 will pass within roughly 1.6 light-years of a star called Gliese 445, currently sitting in the constellation Camelopardalis, in approximately 40,000 years. As Sagan himself put it at the time, the spacecraft will only ever be encountered, and the record only ever played, if there really are advanced spacefaring civilizations out there in interstellar space. But the simple act of launching that bottle into the cosmic ocean, he said, says something very hopeful about life here on this particular planet, regardless of whether it's ever actually found by anyone at all. 40,000 years is, once again, almost nothing on a galactic timescale. It's a single, brief flicker, gone almost as soon as it begins. When measured against the 10 billion-year lifespan of the galaxy, the Voyager probes are now quietly drifting through. And that, more than almost anything else in this entire story, captures the emotional core of the timing problem in a single, concrete image. Two small golden records, carrying greetings in 55 languages, and the voice of a 6-year-old boy, drifting silently through interstellar space for tens of thousands of years, on the extremely narrow chance that someone, somewhere, happens to be in the right place, at the right time, to actually pick them up. Which brings us to what might be the single most important, and most genuinely surprising, development in this entire field over the past several years. A piece of research that flips almost everything we've discussed so far on its head, in the best possible way. In 2021, economist Robin Hanson, the same researcher behind the original 1996 Great Filter essay, teamed up with 3 collaborators, Daniel Martin, Calvin McCarter, and Jonathan Paulson, to publish a formal paper in the Astrophysical Journal titled, "If Loud Aliens Explain Human Earliness, Quiet Aliens Are Also Rare." The paper starts from an observation that, once you actually sit with it, is genuinely strange. If life on Earth had to pass through some number of extraordinarily improbable hard steps in order to eventually produce something like human civilization, then, according to the underlying statistics, the likelihood of that entire sequence happening should have risen sharply over time, meaning it should statistically be far more likely for advanced life to appear later in the universe's history rather than earlier. Hansen and his co-authors calculated that, based on this logic, more than 99% of all advanced life that will ever exist in the universe should be expected to appear after right now, at this point in cosmic history, not before it. In plain language, we appear to have shown up remarkably, almost suspiciously, early. Why would that be? The average star in the universe is expected to keep burning for over 5 trillion years, and the universe itself is currently only about 13.8 billion years old. If you imagine picking a completely random moment across the entire future lifespan of all the stars that will ever exist, and asking when advanced civilizations are statistically most likely to appear, humanity's current position looks less like a random, unremarkable moment, and much more like showing up to a party that's scheduled to run for years, but arriving in the very first few minutes after the doors open. Hansen and his colleagues offered a striking explanation for this apparent earliness, and it's the origin of what's now known as the Grabby aliens model. Their proposal is that there are 2 broad categories of advanced civilizations out there. Quiet civilizations, similar to what humanity has been so far, don't expand aggressively, don't dramatically reshape the visible universe around them, and eventually fade out or die without leaving much of a lasting trace. Loud or grabby civilizations, by contrast, expand outward from their home planet at some significant fraction of the speed of light, visibly and permanently transform the volume of space they pass through, and keep expanding indefinitely until they eventually collide with the expanding territory of some other grabby civilization coming from the opposite direction. According to the model, these grabby civilizations effectively set a kind of deadline for the appearance of new advanced life anywhere within their rapidly expanding sphere of influence. Because once a region of the galaxy has already been claimed and transformed by an earlier grabby civilization, no new civilization can ever independently arise there afterward. Hansen's model suggests this dynamic actually explains humanity's apparent earliness rather elegantly. We exist right now specifically because we happen to be one of the relatively rare civilizations that managed to appear before any grabby civilization's expanding frontier ever reached our particular corner of the galaxy. According to the model's calculations, we may encounter the leading edge of that kind of civilizational expansion at some point within roughly the next billion years, and the same research estimates our own odds of eventually becoming a grabby civilization ourselves before that meeting happens, at something like 1 in 10,000. The Grabby aliens model has plenty of critics within the scientific community, and it's worth being upfront about that rather than presenting it as settled fact. Some researchers have pointed out that the model assumes every habitable planet requires the exact same number of hard evolutionary steps to produce intelligent life, an assumption that may not hold up given how different environmental conditions can be from planet to planet. Others have questioned whether the model's core assumption that grabby civilizations expand at a meaningful fraction of light speed is actually physically realistic, given that humanity's fastest interstellar probes currently travel at only a tiny fraction of that speed. And some critics have argued the entire framework is difficult or impossible to test experimentally, at least with our current technology, since it makes predictions on timescales and distances far beyond anything we can currently verify directly. Even with all of that legitimate scientific pushback, though, the Grabby aliens model represents something genuinely new in this decades-old debate. A serious, mathematically rigorous attempt to explain not just why the universe might be silent, but why we, specifically, might have arrived at this particular moment in cosmic history in the first place, rather than some other moment entirely. There's one more hypothesis worth walking through in detail, because it ties the timing problem and our own radio footprint together more directly than almost anything else we've covered. It's known as the contact era hypothesis, proposed by physicist Amri Wandel of the Raqqa Institute of Physics at the Hebrew University of Jerusalem. Wandel's argument is that visits or probes from putative alien civilizations have a very low probability of reaching us until a civilization has been broadcasting long enough to actually be noticed by someone capable of responding. Under his framework, if biotic, life-bearing planets are common throughout the galaxy, advanced civilizations would preferentially send probes toward planets that show clear techno-signatures, detectable signs of technology, such as radio broadcasts, rather than simply toward any random planet that might merely show biosignatures, chemical signs of biology, without necessarily indicating intelligence. Wandel calculated something called the contact probability, essentially the odds that a nearby civilization is close enough to have already detected Earth's earliest radio emissions and sent a probe that could plausibly have already arrived here by now. His conclusion was that this contact probability for Earth, right now, is very low, unless intelligent, technological civilizations turn out to be extraordinarily abundant throughout the galaxy. But Wandel also pointed out something important and genuinely hopeful buried inside his own math. Because our radiosphere, the expanding bubble of detectable radio signals we've discussed throughout this entire video, keeps growing outward every single year, our own contact probability is also continuously increasing over time, even if it started out vanishingly small. We are, quite literally, becoming more detectable with every passing year, whether we mean to or not, simply by continuing to exist and continuing to use technology that leaks into space. It's worth stepping back at this point and placing all of these different explanations side by side, because seeing them together really does change how the entire puzzle feels. There's the rare Earth hypothesis, formally proposed by researchers Peter Ward and Donald Brownlee in the year 2000, which argues, in direct contrast to everything Kepler's data seems to suggest, that truly habitable planets, and especially planets capable of producing complex, intelligent life, may actually be far rarer than we currently assume, once you account for all the specific astronomical and geological coincidences that made Earth itself so unusually well suited to life. There's the sustainability solution, associated with researchers like Milan Cherkovich and others, which suggests that galactic colonization on the scale Michael Hart originally imagined back in 1975 may simply be far too expensive, too resource-intensive, or too environmentally destructive for any sufficiently wise, long-lived civilization to actually attempt, meaning advanced civilizations might exist in abundance while deliberately choosing never to expand outward the way Hart's original argument assumed they would. And there's an entire body of work applying percolation theory, a branch of mathematics originally developed to study how fluids spread through random, porous materials, to the question of how civilizations might spread, or fail to spread, across a galaxy, with some researchers proposing that expanding civilizations might form something like an infinite, interconnected cluster under the right conditions, while civilizations that fall outside that cluster remain permanently isolated and alone, regardless of how many other civilizations exist elsewhere in the same galaxy. None of these explanations, on their own, manages to fully account for everything we currently observe, or rather, fail to observe. And that's actually one of the more interesting and more honest conclusions to draw from decades of work on this problem. There is probably no single, tidy explanation. It's entirely possible that several of these dynamics are all operating simultaneously, layered on top of each other, compounding one another in ways that make detection even less likely than any single hypothesis would suggest on its own. Maybe habitable planets really are common, exactly the way Kepler's data implies. But maybe the jump from simple life to genuinely intelligent technological life really is astonishingly rare, exactly the way the Great Filter framework worries about. And maybe, on top of both of those factors, the civilizations that do successfully clear every single one of those hurdles only remain detectable, broadcasting loudly enough and consistently enough to be noticed by anyone else for a comparatively short window of time, exactly the way the Drake equation's L variable and the entire timing-based family of explanations suggest. Stack all three of those factors on top of each other, and a silent, seemingly empty sky stops looking mysterious at all. It starts looking almost mathematically inevitable, the natural, unavoidable consequence of a universe this large, this old, and this indifferent to the precise scheduling of the civilizations scattered somewhere across it. Let's actually sit with what that means, because it's easy to hear all of these numbers and statistics and let them wash over you without really feeling the weight of what they're describing. Every single one of the ideas we've walked through so far, the interdice hypothesis, the burnout model, the Great Filter, the Grabby aliens model, is ultimately describing the same basic emotional situation from a slightly different angle. Somewhere out there, quite possibly, an entire civilization rose from nothing, built cities, developed art, argued about the meaning of their own existence, looked up at their own night sky, and wondered the exact same thing we wonder, and then, eventually, fell silent, forever, having never once received an answer to their own version of this question. And somewhere else out there, quite possibly, an entirely different civilization hasn't even been born yet, is still nothing more than loose organic molecules drifting in some primordial ocean on a planet we haven't discovered, waiting for a few more billion years of evolution to slowly turn that raw chemistry into curiosity and eventually into a telescope pointed back at us, long after every trace of humanity itself has vanished from the universe entirely. That's not a comforting thought, exactly, but it's also not the same thing as being told we're completely alone, which is, in its own strange way, an even lonelier idea. Being told the universe is empty is one kind of sadness, a simple, flat kind. Being told the universe might be absolutely full, teeming with civilizations across its entire 10 billion year history, but that we happen to be experiencing our own brief moment of consciousness during one of the vanishingly rare gaps between them, carries a completely different emotional texture. It's less like standing alone in an empty room, and more like walking through a house where you can somehow tell, just from the feel of the place, that people used to live there once, and that people will live there again someday, just never, unfortunately, at the exact same moment you happen to be standing inside it yourself. To really appreciate how long humanity has actually been asking this question in a scientific, rather than purely philosophical way, it helps to go back even further than the wow signal, back past Frank Drake's 1961 equation, all the way to the actual beginning of organized SETI research itself. In September of 1959, two physicists, Giuseppe Cocconi and Philip Morrison, published a short but enormously influential paper in the journal Nature titled Searching for Interstellar Communications. That paper is now considered one of the foundational texts of the entire field, and it directly inspired a young astronomer named Frank Drake, then working at the National Radio Astronomy Observatory in Green Bank, West Virginia, to actually attempt something no one had ever seriously tried before. On April 8, 1960, Drake climbed up into the receiver housing of an 85-foot radio telescope at Green Bank before sunrise and pointed it at a nearby sun-like star called Tau Ceti, roughly 11 light-years from Earth. He named the project Project Ozma, after the princess who rules the fictional land of Oz in L. Frank Baum's novels, a nod to a faraway, difficult-to-reach place populated by strange and exotic beings. Drake tuned the receiver to 1420 MHz, the same hydrogen line frequency that would later show up in the WOW signal 17 years afterward, reasoning that any advanced civilization attempting to signal across interstellar distances would almost certainly recognize this frequency as a kind of universal, physics-based standard. From April through July of 1960, for about 6 hours a day, Drake and his small team listened first to Tau Ceti, and then to a second nearby sun-like star, Epsilon Eridani, also roughly 11 light-years away. The entire project cost approximately $2,000 in equipment. At one point, the team did pick up a strong, pulsed signal that briefly sent the chart recorder's pen swinging wildly, exactly the kind of thing they were hoping to find, before it turned out to be nothing more than a passing high-altitude aircraft, quite possibly a secret military reconnaissance plane. Over roughly 150 total hours of listening, Drake's team detected no extraterrestrial signals at all. But Project Ozma is still remembered today as the true beginning of modern SETI, the very first time humanity systematically pointed an instrument at another star and specifically listened for a deliberate answer. It's worth sitting with that timeline for a moment, because it reinforces everything we've already discussed about how short our own window of listening has actually been. Cocconi and Morrison's foundational paper came out in 1959. Drake's first actual listening attempt happened in 1960. The Drake equation itself followed in 1961. The WOW signal came 17 years after that, in 1977, the same year the Voyager probes launched carrying their golden records out into the silence. Breakthrough Listen, the most ambitious and best-funded search effort in history, didn't begin operating until 2016. From Cocconi and Morrison's original paper to right now, we are talking about a span of a little under 70 years. 70 years, compared to a galaxy that is roughly 10 billion years old, is not just a small number. It's a number so small that if you tried to represent the galaxy's entire history as a single day, 24 hours long, all of organized human SETI research, every single radio telescope pointed at every single star, every dollar spent, every hour of data collected, would occupy considerably less than 100,000th of a single second. We have been listening for what amounts to a single, brief flicker, and we are, quite understandably, disappointed that we haven't yet heard anything back. The search hasn't stood still since Breakthrough Listen came online either, and one of the most recent developments deserves a place in this story, because it shows exactly how this field keeps evolving in real time, mistakes, corrections, and all. In 2025, astronomers using the James Webb Space Telescope announced they had detected chemical fingerprints in the atmosphere of an exoplanet called K2-118b, located roughly 120 light-years away in the constellation Leo, orbiting a red dwarf star. The molecules in question, dimethyl sulfide and possibly dimethyl disulfide, are significant because on Earth they are produced almost exclusively by biological life, primarily by marine phytoplankton drifting in our oceans. The announcement, published in the astrophysical journal Letters and led by astronomer Niku Madhusudan at the University of Cambridge, was quickly reported as the strongest evidence yet that life might exist on a planet outside our own solar system. But almost immediately, other scientists began pushing back. Researchers pointed out that laboratory experiments had already demonstrated these same molecules can form through entirely non-biological chemical processes under the right conditions, and that dimethyl sulfide has even been detected drifting through comets and interstellar clouds, places with no connection to life whatsoever. A follow-up analysis led by NASA in the summer of 2025 confirmed that K2-18b does appear to be a genuinely water-rich world with a complex atmosphere, but found no conclusive evidence that the disputed molecules were actually present after all. As one of the researchers involved put it, in a field like this, context matters enormously, and being deeply skeptical of your own most exciting results is simply how good science has to work. That whole episode, unfolding in real time over the course of about a year, right up through the middle of 2025, is a small, perfect snapshot of exactly the situation we've been describing this entire video. Excitement, followed by scrutiny, followed by walking the claim back to something more careful and more honest. It's the WOW signal story playing out again, on a faster timescale, with better instruments, and it's a reminder that the search for a genuine, confirmed answer to Fermi's original question is still very much ongoing, messy, contested, and very much alive, right up to the present moment. Let's take a step back now and try to hold the whole shape of this argument in your mind at once, because that's really the only way any of this fully lands. We know the raw ingredients for life appear to be common. Kepler alone identified thousands of planet candidates, hundreds of them sitting inside their star's habitable zone, and statistical extrapolations from that same data suggest something like a third of all Sun-like stars in the galaxy could host a rocky, potentially habitable world of their own. We know the galaxy is old, roughly 10 billion years old, more than twice the age of our own solar system, which means there has been an enormous amount of time for life to have arisen, developed, and either flourished or vanished somewhere else, long before Earth even finished forming. We know our own species has existed for roughly 200,000 years, but has only possessed the technology to detect or send interstellar signals for a little under 70 years, an almost unmeasurably small fraction of our own species' total lifespan, let alone the galaxy's. We know our radio footprint, the total physical evidence of our own existence currently detectable from outside our solar system, covers something on the order of 0.002% of the Milky Way. And even that tiny footprint is already fading in strength as we shift toward more efficient digital technology. We know that in nearly 70 years of dedicated, organized listening, starting with Frank Drake's $2,000 experiment in 1960, and running all the way through a $100 million initiative backed by some of the wealthiest people on the planet, we have found exactly one unexplained signal that still can't be dismissed as noise or interference, a signal that lasted just 72 seconds and never repeated. And we know, thanks to Robin Hansen's Grabby aliens research published in 2021, that if intelligent life really does require passing through some number of extraordinarily improbable hard steps, then simple statistics suggest we should have expected to appear later in cosmic history than we actually did, not earlier, which raises the genuinely strange possibility that we are, in some meaningful sense, unusually early to whatever this is. Put all of that together, and the silence stops feeling like proof that we're alone. It starts feeling like exactly what you would expect to find if the universe really is full of civilizations, scattered unevenly across 10 billion years of galactic history, each one experiencing its own brief window of visibility, and almost none of those windows ever happening to land on top of each other by pure chance. There's a question worth sitting with at this point, one that tends to come up naturally once you've walked through all of this material, and it's a question that turns the entire conversation around and points it directly back at us. If the Great Filter really is out there somewhere, sitting between simple life and a fully expansive spacefaring civilization, and if we genuinely don't know whether we've already cleared it or whether it's still waiting somewhere ahead of us, what would that actually mean for humanity's own future? Robin Hansen's original 1996 essay was explicit about this part of the argument, and it's worth repeating plainly because it's easy to lose the emotional weight of it inside all the statistics. If the Great Filter sits behind us, in our evolutionary past, then the fact that space around us currently looks empty is actually good news in a strange, roundabout way. It would mean the hardest, most improbable step in the entire process, the step that stops nearly everyone else, is something we've already survived without even realizing how close we came to never existing at all. Under that scenario, humanity's future, statistically speaking, looks genuinely bright. We'd have a real, meaningful chance of eventually expanding outward ourselves, filling some portion of this same silent galaxy with our own light and our own signals, exactly the kind of civilization Michael Hart imagined back in 1975 when he first tried to explain why interstellar colonizers should already be visible if they existed at all. But if the Great Filter is still out there ahead of us, somewhere in our future rather than our past, the same silence starts to look considerably less comforting. It would mean that every other civilization that ever reached roughly our own level of technological development, agriculture, writing, industry, electricity, radio, nuclear power, eventually ran headlong into some kind of barrier severe enough to stop them from ever becoming detectable across interstellar distances, and it would suggest we're likely heading toward that exact same barrier ourselves, whatever it eventually turns out to be. Hansen himself was careful to point out that this possibility doesn't necessarily mean sudden, dramatic extinction, the kind of thing you'd see in a disaster film. It could just as easily mean a slower, quieter kind of filtering, technological stagnation, self-imposed isolation, or a societal choice to simply stop reaching outward the same way the asymptotic burnout researchers described, choosing long-term stability over continued expansion, and therefore becoming exactly the kind of quiet, undetectable civilization this entire video has been describing all along. Nobody currently knows which of those two scenarios we're actually living inside, and that uncertainty is, frankly, part of what makes this whole subject so difficult to simply set aside once you've really thought it through. Every one of the potential hard steps Hansen originally identified back in 1996, the emergence of self-replicating molecules from raw chemistry, the jump from single-celled to complex multicellular life, the development of genuine intelligence, the invention of language and tool use, remains only partially understood by modern science, even decades later. We don't actually know how rare or how common any single one of those transitions really is, because we still only have exactly one confirmed example of the entire sequence happening anywhere in the universe, right here on Earth. Until that changes, until we either find clear evidence of life having independently arisen somewhere else, or find increasingly strong evidence that we are, in fact, entirely alone, every one of those steps remains a giant, unanswered question mark hanging over our own species' long-term future. This is part of why the Grabby aliens research from 2021 landed with such force inside the scientific community when it was first published. It didn't just offer another abstract explanation for the general silence in the sky. It offered a specific, mathematically grounded reason to believe that whatever the Great Filter actually is, we may have already cleared the hardest part of it, simply by existing this early in cosmic history at all. If truly Grabby, expansionist civilizations are common enough to eventually fill most of the universe, and if the sheer difficulty of the hard steps required to produce intelligent life explains why advanced civilizations should statistically appear later rather than earlier, then our own early appearance becomes a small, quiet piece of genuinely encouraging evidence. Not proof, not certainty, but a mathematically coherent reason to think that the very fact you're able to sit here right now and think about any of this at all might be a meaningfully hopeful sign about what still lies ahead for us, rather than a warning about what's still coming. Of course, all of this remains deeply uncertain, and every serious researcher working in this field, from Robin Hansen to Frank Drake to the scientists currently poring over the K2-18b data, would tell you the same thing without hesitation. We simply don't have enough data yet to know for certain. One single confirmed detection, anywhere, at any distance, of a genuinely artificial signal or a genuinely biological signature would immediately reshape every single one of these models overnight. And one more century of continued silence, gathered with increasingly sensitive instruments across an increasingly large portion of the sky, would meaningfully shift the odds in the other direction, making some of these more pessimistic explanations look considerably more plausible than they do today. Either way, the only real path forward is the same one humanity has been walking since Cocconi and Morrison published their original paper back in 1959. Keep looking, keep listening, keep refining the instruments, and keep being honest about exactly how much and how little we currently actually know. There's another angle to this entire problem worth walking through carefully, because it deals directly with one of the most persistent and most cinematic fears people have about the possibility of contact, and it turns out to connect back to timing in a way that isn't always obvious at first. The idea of self-replicating machines, devices capable of building copies of themselves using local raw materials without ongoing human involvement, wasn't originally proposed as a tool for interstellar exploration at all. It emerged from theoretical work on automata and computation done in the mid-20th century, and it was later adapted by astronomers and physicists thinking specifically about how a sufficiently advanced civilization might explore, or potentially dominate, an entire galaxy without needing to build and launch a separate spacecraft for every single star system. A probe capable of arriving at a new star system, mining the raw materials available there, whether from asteroids, moons, or planets, and using those materials to construct several new copies of itself, could theoretically spread across an entire galaxy in a comparatively short amount of time, with the total number of active probes growing exponentially rather than linearly. This is the exact concept David Brin was drawing on in his 1983 essay when he described the Berserker hypothesis, the possibility that a single hostile civilization, having built exactly this kind of self-replicating probe network with orders to seek out and eliminate emerging technological life, could methodically silence an entire galaxy's worth of civilizations over time, without the original civilization needing to do anything more after the initial launch. But here's the part that connects this idea back to everything we've already covered about timing rather than distance. Even a genuinely hostile, self-replicating probe network, spreading exponentially across a galaxy, would still take real time to physically travel between star systems, time governed by the same basic laws of physics that limit every form of travel we know about. Depending on how fast such probes could realistically move, filling an entire galaxy could take anywhere from a few 100,000 years to several million years, according to various theoretical estimates researchers have proposed. That's genuinely fast on a cosmic scale, fast enough to explain why we might not see evidence of multiple independent, expanding civilizations coexisting peacefully at the same time. But it's not instantaneous, and it doesn't erase the fundamental timing problem so much as it adds an additional layer on top of it. A probe network launched 3 million years ago by a civilization that has since gone silent itself, for whatever reason, might have already swept through our region of the galaxy long before humans ever existed, left no obvious trace because there was, at the time, nothing here yet worth eliminating, and continued onward, or eventually broken down, or simply run out of updated instructions, long before we ever had a chance to notice it was here at all. The timing problem doesn't disappear just because a hypothesis involves something as dramatic as hostile robotic probes. If anything, it becomes even more pronounced, because now, you're not just asking whether two civilizations' broadcasting windows happen to overlap. You're asking whether an automated system, launched by a civilization that might itself be long gone, happened to pass through a specific, tiny region of space during the exact multi-million-year window when anyone was actually there to notice it. It's worth returning, one more time, to that calendar metaphor we opened this whole discussion with, because by this point in the conversation, it carries a lot more weight than it did at the beginning, now that we've actually walked through the real numbers behind it. Picture that same single calendar year again, January 1st as the Big Bang, midnight on December 31st as this exact moment. Kepler's data suggests that somewhere across that entire year, on hundreds of billions of individual planets scattered throughout our metaphorical galaxy, the basic ingredients for life, habitable worlds orbiting stable stars, have probably existed in genuine abundance for a very long stretch of that calendar, potentially going back to sometime in the spring or early summer of that year, whenever the first generation of stars capable of hosting rocky, water-bearing planets first began to form. If the Great Filter really does sit somewhere between simple chemistry and intelligent life, as Robin Hanson originally proposed back in 1996, then most of those hundreds of billions of planets, across that entire calendar year, may have simply never produced anything more complex than basic microbial life, no matter how much time passed. But on the handful of planets that did eventually clear that filter, going all the way from simple chemistry to genuine intelligence, the actual window of technological visibility of anyone home on that planet capable of building a radio telescope, or a Voyager probe, or a self-replicating spacecraft would have been almost impossibly brief. Not a season, not even a full day. On our own planet's calendar equivalent, it's been less than a single second, and we've only actually been paying attention, actively listening rather than simply broadcasting by accident, for a small fraction of even that single second. Multiply that briefness across a galaxy full of independently evolving civilizations, each one showing up on its own random day, at its own random hour, for its own random handful of seconds, somewhere across that entire calendar year, and the silence stops requiring any explanation involving hostility, or hiding, or deliberate secrecy at all. It becomes something closer to simple probability, playing out exactly the way probability tends to play out at a truly enormous scale, unevenly, unpredictably, and almost never in a way that produces the kind of neat, simultaneous overlap that would actually let two separate civilizations notice each other. Let's bring this all the way back down to something small and human for a moment. Because it's easy to get lost inside numbers this large: 10 billion years, 400 billion stars, 99% probability figures, and lose track of what any of it actually feels like from the inside. Think about the very first moment Jerry Amon sat down at his desk in 1977, scanning through pages of printed data the way he had done countless times before, night after night, mostly finding nothing but ordinary background noise. And then, suddenly, there it was, a signal strong enough, clean enough, unusual enough, that his hand moved almost on instinct, circling it, writing a single word in the margin. For 72 seconds, whatever produced that signal was, in some sense, present, detectable, real, at least as real as anything measured by an instrument can be. And then it was gone, and it never came back. Not that night, not in the following weeks, not across 20 more years of the same telescope, listening to the same patch of sky, not across decades of follow-up searches, using instruments Amon himself never could have imagined in 1977. Whatever caused that signal, whether it was some poorly understood natural phenomenon, or a stray reflection of something human-made, or, just possibly, an actual transmission from somewhere else entirely, it occupies exactly the kind of narrow, unrepeatable window this entire video has been describing. It showed up, briefly, during the exact sliver of time someone happened to be listening, and then it was gone, absorbed back into the overwhelming silence surrounding it on every side. That's the emotional core of everything we've walked through together. Not a story about aliens refusing to answer, or hiding from us, or being too far away to ever reach. A story about timing, about how difficult it actually is for two separate, independent flickers of activity, scattered randomly across 10 billion years and 400 billion stars, to ever land on top of each other long enough to notice one another at all. It's the same reason two people can walk through the exact same crowded train station, on the exact same day, separated by only a few minutes, and never once cross paths, even though both of them were there, both of them were real, and both of them, in some small way, were looking for exactly the kind of connection the other one might have offered. This idea has quietly shaped an enormous amount of the way we think and tell stories about extraterrestrial life, even when most people encountering those stories don't necessarily know the underlying science behind them. Every work of fiction that imagines humanity discovering the ruins of a long-dead alien civilization, rather than a living one, is drawing, whether consciously or not, on exactly this timing problem. Every story that imagines a signal arriving from a star that burned out millions of years before the signal ever reached us is grappling with the same basic mathematics we've spent this entire discussion working through. The idea that the universe might be full of ghosts, rather than full of neighbors, has become one of the more quietly haunting threads running through decades of science fiction, television, and film, precisely because it captures something true about the actual physics and statistics involved, even when the specific stories themselves are invented. And it's worth remembering, sitting with all of this, that humanity's own contribution to this enormous, scattered, mostly silent conversation is still actively being written, right now, in real time, whether we think about it consciously or not. Every year that passes, our radio bubble expands by another light year in every direction. Every new radio telescope we build, every new satellite we launch, every new signal we send, whether by accident through ordinary broadcasting or on purpose through something like the Arecibo message, adds one more small piece to the total record of our own civilization's brief window of visibility. We don't know, and probably never will know with certainty, whether anyone else's window will ever overlap with ours. But the act of looking, the act of building bigger telescopes and more sensitive receivers and more ambitious search programs like Breakthrough Listen, is itself a kind of quiet defiance against the odds we've spent this entire video laying out. It's a refusal to simply accept the silence at face value, and an insistence, even in the face of genuinely discouraging statistics, on continuing to listen anyway, on the off chance that this particular year, this particular decade, this particular narrow slice of cosmic time, turns out to be the one where two separate flickers of light, separated by an entire galaxy, and possibly by millions of years of history, finally happen to land on top of each other after all. Before we bring all of this together, it's worth walking back through the actual timeline of this story one more time, slowly, start to finish. because seeing the dates lined up in order really does drive home just how compressed and recent almost the entire history of this search actually is. It starts, in a purely observational sense, in 1895, with the first radio transmission ever achieved, the culmination of decades of work by multiple inventors across different countries. It picks up meaningfully on December 24, 1906, when Reginald Fessenden made the first intentional, powerful radio broadcast, including that recording of his own violin playing, marking the true beginning of Earth's radio bubble expanding outward into space. Then, in September of 1959, physicists Giuseppe Cocconi and Philip Morrison published their foundational Nature paper, Searching for Interstellar Communications, laying the theoretical groundwork for an entire scientific field that didn't fully exist yet. On April 8, 1960, Frank Drake pointed an 85-foot radio telescope at Tau Ceti and Epsilon Eridani in Project Ozma, humanity's first organized, systematic attempt to listen for a deliberate reply from another star. Around 1950, roughly a decade before that, military radar and high-powered analog television broadcasting had already begun ramping up dramatically, creating the stronger, more detectable core of what would eventually become our radio bubble. In the summer of 1950, that same general period, Enrico Fermi asked his now famous question over lunch at Los Alamos, a full decade before anyone actually tried to answer it observationally. In 1961, Drake formalized his equation at the Green Bank meeting, giving the entire field a mathematical framework to organize its guesses. In 1973, John Ball proposed the zoo hypothesis in the pages of Icarus. In 1974, the Arecibo message became humanity's first deliberate, targeted transmission aimed at another star system. In 1975, Michael Hart formalized the paradox itself into the rigorous argument that still bears its structure today. In 1977, two things happened within months of each other that still define this entire field. The WOW signal was detected on August 15th, and the Voyager probes launched carrying their golden records out toward the edge of the solar system and beyond. In 1983, David Brin published his influential essay on the Great Silence, introducing the Berserker hypothesis to a wider audience. In 1987, the interdice hypothesis was published in Icarus, formally proposing the timing-based explanation that sits at the very center of everything we've discussed today. In 1996, Robin Hanson introduced the Great Filter in his September essay. In 1997, the Big Ear telescope, after 22 continuous years of searching, was finally shut down. In 2000, Ward and Brownlee proposed the Rare Earth hypothesis. In 2009, NASA launched the $600 million Kepler Space Telescope. In 2015, Breakthrough Listen was announced by Yuri Milner and Stephen Hawking, beginning full operations the following year. In 2017, Sandberg, Armstrong, and Cherkovich proposed the aestivation hypothesis. In 2020, Alberto Caballero identified a candidate source star for the WOW signal using Gaia data. In 2021, Robin Hanson and his colleagues published the Grabby aliens model, arguing that humanity's early appearance in cosmic history might itself be meaningful evidence. In 2022, Breakthrough Listen searched that candidate star and found nothing. And in 2025, astronomers using the James Webb Space Telescope detected, and then partially walked back, a possible biosignature on the exoplanet K2-18b, a reminder that this search is still very much active, still very much uncertain, and still very much unfolding in real time, right up to this exact moment. Laid out end to end like that, the entire history of humanity's organized search for evidence of anyone else out there spans a little under 70 years, from Cocconi and Morrison's 1959 paper to today, 70 years. Against a galaxy that took roughly 10 billion years to reach its current form, and that will keep going, by most estimates, for trillions of years into the future, as the average star continues burning long after our own sun has faded away. We have been listening for what amounts to a single held breath, measured against the true lifespan of the universe we're trying to listen across. And it is, on reflection, remarkable that we've found even one genuinely unexplained anomaly in that time. let alone that we should have expected to find anything more than that at all. So where does all of this actually leave us, sitting here right now, in the middle of whatever tiny sliver of cosmic time we happen to occupy, watching a video about a question that has genuinely puzzled some of the smartest people who have ever lived? A few things are worth holding on to, carefully, as we bring this all together. First, the search hasn't stopped, and if anything, it's better funded, more sophisticated, and more scientifically rigorous right now than at any previous point in human history. Breakthrough Listen alone represents an unprecedented combination of money, telescope time, and computing power devoted specifically to this question, and it's just one part of a much larger, ongoing effort that includes everything from the James Webb Space Telescope's atmospheric analysis of distant exoplanets to ground-based radio surveys scanning enormous stretches of sky for anything resembling an artificial signal. Every year that passes, our instruments grow more sensitive, our methods for filtering out false positives grow more refined, and the total portion of the sky we've actually searched in any meaningful, systematic way continues to grow, even though, as more than one researcher in this field has pointed out, we've still only sampled a genuinely tiny fraction of our own galaxy, let alone the universe beyond it. Second, our own signal keeps growing too, even as its underlying character continues to change. Every single year that goes by, Earth's radio bubble expands by another light year in every direction, carrying with it whatever we happen to be broadcasting during that particular year, whether that's a presidential address, a football game, or simply the accumulated background hum of billions of people going about their ordinary lives. Somewhere out there, decades or centuries from now, a thin shell containing footage and signals from the middle of the 20th century will still be sweeping outward past stars we haven't even named yet, long after everyone who was ever involved in creating those original broadcasts has been gone for generations. Third, and this might be the single most important point in this entire discussion, the timing problem doesn't mean the search itself is pointless or naive or a waste of the enormous resources currently being poured into it. It means the search has to be approached with a kind of patience that goes well beyond ordinary human patience, the kind most of us practice in our daily lives. It means genuinely internalizing the idea that the absence of a confirmed signal today doesn't actually tell us very much about what may have happened a million years ago on some world we'll never know existed, or what might happen a million years from now on some world that hasn't even formed yet. It means learning to treat the silence itself as a genuine piece of data, rather than as a final, disappointing answer to the entire question. Because here's the thing about a party where some guests arrive too early and others leave too late, and almost nobody's visit actually overlaps with anybody else's. From the outside, walking past at any single given moment, it can look completely empty. No noise spilling out into the street, no lights on behind the windows, no visible sign that anyone was ever there or that anyone is ever going to show up later that same night. And yet the guest list, over the full span of the evening, might be enormous. The story of that party, stretched out across its entire duration, might be rich and strange and genuinely long, full of people who came and went at completely different hours, who never once crossed paths with one another, who each quietly experienced the whole thing as a private, solitary evening, entirely unaware of everyone else who also showed up, just on a different night, at a different hour, having no way of knowing the party was ever anything other than empty and still. That may well be what the universe actually is. Not empty, not silent because there was never anyone there to begin with. Silent because nearly everything that was ever there already finished saying what it had to say, long before we arrived, and because nearly everything that will eventually be there hasn't started talking yet, hasn't even been born yet, is still just loose chemistry drifting somewhere in the dark, waiting for its own turn to come around. And we happen to be standing right in the gap between those two vast, overlapping conversations, one already finished, one not yet begun, listening as hard as our instruments currently allow us to listen, out toward a room that was, and almost certainly will be again, anything but quiet, even if it never once, in all the time we get to spend inside it, happens to sound that way to us. Maybe that's the real answer to Fermi's question, 75 years after he first asked it over lunch. without ever writing a single word about it down. Maybe the universe was never actually silent at all. Maybe it's simply been talking, this entire time, in a language built out of timing rather than distance. A language where the biggest obstacle was never how far apart we are, but when, exactly, each of us happened to show up. And maybe the most honest thing anyone can say, standing here at the end of everything we've walked through together tonight, is that we genuinely don't know yet whether we arrived too early, or whether everyone else simply left too late, or whether, somewhere out there right now, on some planet orbiting some star we haven't even named, somebody else is asking the exact same question we've spent this entire video asking, at the exact same moment, in a universe large enough and old enough and patient enough to eventually let both of those questions be answered, even if neither one of us is around anymore to actually hear it. There's one last piece of this worth sitting with before we close things out, because it's easy, after walking through an hour's worth of statistics and hypotheses and dates, to feel like this entire subject is something that only exists inside research papers and observatory control rooms, far removed from anything an ordinary person could actually experience for themselves. But that's not really true, and it's worth saying plainly before we finish. The next clear night you have the chance, step outside for a few minutes and actually look up. Not at your phone, not through a telescope necessarily, though that helps. Just up, with your own eyes, at whatever portion of the night sky happens to be visible from wherever you are. Somewhere in that sky, invisible to the naked eye, but very much real, Earth's own radio bubble is quietly expanding outward in every direction, carrying pieces of the 20th and 21st centuries past stars most of us will never learn the names of. Somewhere in that same sky, according to researchers using data from the Kepler mission, there are very likely tens of billions of planets, scattered among the visible stars and the countless more you can't see at all, some fraction of which may have once hosted, or may someday host, or may right now be quietly hosting, something capable of looking back in our direction and wondering the exact same thing we're wondering. Vega, one of the brightest stars visible on a clear night depending on the season and your location, has already been reached by the strongest signals humanity broadcast during the middle of the 20th century. Tau Ceti and Epsilon Eridani, the very first two stars Frank Drake ever pointed a telescope at back in 1960, are still out there, roughly 11 light-years away, exactly where they've always been, still not having answered, but also, as far as we currently know, never having said no. None of this requires you to believe with certainty that anyone is actually out there. It doesn't require you to believe we're alone either. What it asks, if anything, is simply that you hold both possibilities at once, the way the best available science currently allows us to, and recognize that the silence we've been describing this entire video isn't necessarily an answer. It's a measurement, taken during one extraordinarily brief window of time, by one extraordinarily young civilization, using instruments that have only existed for a fraction of the time the questions themselves have been sitting there, waiting to be asked. 70 years of listening, against 10 billion years of galactic history, and against however many trillions of years still remain ahead of us, is not evidence of absence. It's barely evidence of anything at all, beyond the fact that we started looking, and that we haven't stopped. That, in the end, might be the entire point of everything we've covered here tonight. Not a final answer, because there isn't one yet, and there may not be one for a very long time, possibly not within any of our own lifetimes, possibly not within our species' entire lifetime, however long that ultimately turns out to be. What we actually have, right now, tonight, is a question, inherited from a lunchtime conversation at Los Alamos in the summer of 1950, refined and expanded by 70 years of careful, patient, often disappointing research, and handed down to every single person who has ever looked up at a clear night sky and wondered whether anyone up there happened to be looking back. The universe may very well be quiet because everyone leaves too late, or arrives too early, or simply never quite manages to line up their own brief moment of visibility with anyone else's. But quiet isn't the same thing as empty. And as long as there's still a difference between those two words, there's still a reason to keep listening. It's worth asking, honestly, what would actually change if that silence were ever finally broken? Not in a dramatic, cinematic sense, but in the practical, scientific sense, that researchers in this field actually think about. A single confirmed signal, verified independently by multiple observatories the way any serious scientific claim requires, wouldn't just answer Fermi's original question. It would immediately answer a whole cascade of questions sitting behind it. It would tell us something about L, the Drake equation's longevity variable, the number scientists have been forced to guess at for over 60 years, with essentially no real data to work from. It would tell us something about where exactly the Great Filter sits, whether behind us or ahead of us, since a confirmed detection would mean at least one other civilization had successfully cleared every single step required to become detectable, which would meaningfully shift the odds for our own future in one direction or the other. And it would tell us something about timing itself, about just how rare or how common it actually is for two separate civilizations' brief windows of visibility to overlap, since the mere fact of detection would mean it had already happened at least once, somewhere, to somebody. That's part of why the K2-18b controversy and the WOW signal before it and every other near-miss and false alarm scattered across this entire 70-year history generates as much genuine excitement as it does within the scientific community, even when, almost every single time, it eventually gets walked back or explained away by some more mundane cause. Each one of those moments represents a tiny crack of light in what has otherwise been a remarkably consistent, remarkably long silence, and each one forces researchers to seriously entertain, if only for a few days or weeks, the possibility that this particular moment, this particular signal, this particular measurement might turn out to be the one that finally breaks the pattern. So far, every single one of them has eventually resolved back into more mundane explanations, or simply faded into unresolved mystery, the way the WOW signal itself still sits today, 49 years later, neither confirmed nor fully explained away. But there's something worth noticing in the sheer persistence of that pattern too. Despite decades of disappointment, despite a success rate that currently sits at exactly 0 confirmed detections out of every serious search ever conducted, the search itself has never actually slowed down. If anything, it's accelerated, growing from a $2,000 experiment involving one astronomer and one borrowed radio telescope in 1960 to a coordinated, multi-institution, $100 million initiative spanning multiple continents and multiple types of instruments by the 2020s. That kind of sustained, growing investment in the face of decades of silence says something meaningful about how seriously the scientific community continues to take this question, even without a single confirmed success to point to as proof that the effort is worthwhile. It suggests that the people closest to this research, the ones who understand the statistics and the timescales better than almost anyone else on the planet, still believe the silence is more likely to be a matter of timing and probability than a final, settled answer. And that belief, however cautious and heavily qualified it remains within the scientific literature itself, is really what this entire video has been trying to communicate from the very beginning. Not a confident prediction that we will find something tomorrow, or next year, or even within our own lifetimes. Just a genuinely well-supported case, built on real mathematics, real data from missions like Kepler, and real historical patterns stretching back to a lunchtime conversation in 1950, that the emptiness overhead might be telling us far less about who's out there than it initially seems to. It might simply be telling us when. So the next time you hear someone say the universe looks empty, or that the silence overhead is proof we're the only ones who ever showed up, it's worth remembering everything we've walked through together tonight. Remember Fermi's offhand question at a lunch table in 1950, a question he never once bothered to write down himself. Remember Frank Drake's $2,000 experiment in 1960, and the equation he built the following year, with a single variable, L, that nobody has ever been able to fill in with real confidence. Remember Jerry Amon circling 72 seconds of unexplained data in red ink in 1977, the same year 2 golden records carrying greetings in 55 languages left the solar system for good. Remember the 9 uncertain steps in Robin Hansen's Great Filter, and the strange, quietly hopeful mathematics behind his 2021 argument that we may have arrived unusually early to a universe that still has trillions of years left to run. Remember that our own radio bubble, everything we've ever broadcast, intentionally or not, still covers only 0.002% of our own galaxy, and that we've only been listening back, in any organized way, for a little under 70 years out of the 10 billion years the galaxy itself has existed. None of that proves anyone else is out there, but none of it proves they aren't either. What it proves, as carefully and as honestly as the current evidence allows, is that silence, on a scale this large, was never guaranteed to mean absence in the first place. It might simply mean that everyone, everywhere, across the entire history of this galaxy, has been arriving fashionably early, or leaving painfully late, and never quite managing, against odds this astronomical, to walk through the same door at the same time. There's a particular kind of comfort, oddly enough, hidden inside all of this uncertainty, if you're willing to sit with it for a moment, instead of rushing past it toward a tidier conclusion. Most of the biggest questions in life come with at least some kind of partial answer attached, even an unsatisfying one. This one doesn't, not yet, and honestly, it might not for a very long time, possibly not within any of our lifetimes, possibly not within our species' entire existence, however long that turns out to be. And yet the not knowing itself carries a strange kind of weight that feels different from ordinary uncertainty. It isn't the uncertainty of a coin flip, where the odds are known and the outcome is simply hidden until the coin lands. It's the uncertainty of two people standing in the same enormous, dark room, each one absolutely certain the other exists somewhere nearby, neither one able to prove it, both listening as carefully as they possibly can for any sound at all, knowing that even total silence, stretching on for hours, wouldn't actually mean the room was empty. It would just mean neither of them has found the right moment yet, in a room large enough and dark enough that finding that moment might take longer than either of them has time to wait. Every telescope pointed at the sky right now, every radio dish quietly logging data at Green Bank or Parkes, or the dozens of other observatories scattered across the planet, every scientist combing through petabytes of breakthrough listen data looking for the faintest hint of a pattern, is, in a very real sense, still standing in that same dark room, still listening, 70 years in and counting. And the fact that they haven't stopped, despite a perfect record of coming up empty so far, might be the single most quietly hopeful detail in this entire story. Not because it guarantees an answer is coming, but because it means the question itself, the one Fermi asked almost accidentally over lunch in 1950, still matters enough, to enough people, that nobody involved has been willing to simply let the silence have the last word. If this is the kind of question that's going to sit with you long after this video ends, quietly turning over in the back of your mind the next time you happen to look up at a clear night sky, that's exactly the reaction we were hoping for, and it's exactly why it's worth sticking around for whatever we dig into next. Because that, ultimately, is the quiet thesis running underneath everything we've covered tonight. From a lunchtime conversation at Los Alamos in 1950, through Frank Drake's borrowed telescope in 1960, through 72 circled seconds in 1977, all the way up to a debated molecule in a distant atmosphere in 2025. The universe has never once told us, definitively, that we're alone. All it has told us, so far, is that nobody has managed to say hello at the exact right moment. Those are two very different sentences, and mistaking one for the other is probably the single easiest way to misread everything this field of research has actually found. The silence is real. The conclusion people tend to draw from it, that nothing is out there making that silence, has never actually been proven, not once, in 70 years of trying. Like this video if it gave you something new to think about. Subscribe if you want more of these deep dives into the biggest unanswered questions science still hasn't cracked, and I'll see you in the next one.